So we will continue to solve problems on chapter 3. Let us wait just some time because some people are still entering the meeting. Okay. So we have a steel test specimen of modulus of elasticity 30 times 10 to the power 6 lb per inch square that is undergoing a compression test and has a starting height of 2 inch and diameter of 1.5 inch. The metal yields at a load of 140,000 lb, given that the yield is determined based on the 0.2% offset method. At a load of 260,000 lb, the height has been reduced to 1.6 inch. First, determine the yield strength, and second, find the flow curve parameters, which are the strength coefficient and the strain hardening exponent. Assume that the cross-sectional area increases in a uniform way during the test. So here, first we are in the case of a compression test. Okay. In case of compression, we know that the stress and strain are negative. But when we write epsilon compression or sigma compression, we can deal with the absolute value. Okay. Now, to start with, we need to find the yield strength. Okay. To find the yield strength, we go back to the definition. So we know that sigma at yield is based on the engineering value, okay, is equal to the force at yield over the initial cross-sectional area A0. Okay, so first, for the yield force, it's given. So they said that the metal is yielding at a load of 140,000 lb. Now, concerning units, here, since they are giving forces in lb and all lengths in inch, so we will have the force in lb and the stress in lb per inch square and the area in inches square. Now, since we know the initial diameter of my specimen, which is 1.5 inch, I can calculate A0 as by using the initial diameter. So it's equal to pi times d0 square over 4. Okay, so this will give us the value of A0. And now we can calculate the value of sigma yield. And here, this is the engineering value. When they talk about yield strength, so this is based on the engineering value. Okay, but we will see after that we need the true value at yield, true stress value, because we will use it to calculate the strength coefficient and strain hardening exponent. So this is for the first question. But in question B, you know that to determine the flow curve parameters, you need 2 points. And in general, we take 2 points between yield and necking. In case here, if you read the problem, you don't have an information about 2 points. You just have information about yield point and one other point corresponding to a load of 260,000 lb, which will lead to a height of 1.6 inch. So yield point can be considered as a point in the strain hardening zone because it is the transition point. Yani it will, the yield point, if you want, will verify the equation of the elastic region, but will also verify the equation of the strain hardening region because it is the point of transition. So if you don't have another choice, it's not wrong to take the yield point as a point of to determine your coefficients. Now, in general, because to be on the safe side, if we have another point, we take the other point because you know that for yield, it's just the starting of this zone. Okay. So in general, if you have any 2 points in between, we prefer to take 2 points in between, far from yield and far from nothing. But a yield point is also can be considered as the first point of this curve, so it should also verify the equation. So it's not wrong to take it as a point. And here we don't have the choice. We should take it because we only know the yield point characteristics and another point characteristic. So if you want to present nearly the curve, it will be something like this. Okay. So for the transition point, this is the yield point, which is the transition between elastic and plastic regime. Now, since they said that the value is given based on the 0.2% offset method, so this corresponds to taking a value of epsilon equals to 0.002. And from here, we draw a parallel line to the elastic region. This method, in general, we use it when we are not sure about the point. Yani the point is not very well defined in the figure. We use this method to determine the yield. And here, I just, it seems that there is a difference because I did it a little bit big for you to see it. But in real case, this line is very, very close to, if you put it to scale, it will be nearly like this, like this. Okay, so the point you will get will be nearly here. But just for you to see, I did a small difference. Okay, so whenever they say the yield is determined based on the offset method, this means that we determine it by drawing this line. Now, why they gave us this information? Because we need to find epsilon at sigma yield. Okay, because we need complete characteristics of this point. So we need to know what is the value of sigma at yield, which was already calculated. So we have calculated together already sigma yield. But to define completely this point, we need also the value of epsilon here, which is called epsilon at yield. Okay. Now to find epsilon at
دكتور
yield, yes.
ليه رسمنا هذا الجراف؟ مش هذا للتنشن؟ مش لازم نرسم جراف
الجراف
الكompression؟
هون نحن عم نرسم الابسوليوت value of compression. اوكي يعني we are
اوكي
drawing sigma compression. وقت اكتب C I take the absolute value function of epsilon. ايه بس اكيد معك حق النكينج part مش موجوده. يعني if you want we will stop somewhere like this. It will be like this. يعني because it's a compression test not a tension test, this part will not be here. Okay, because we don't have necking in compression, and it will be something like this. It will continue until to increase until fracture. Okay, this is the only difference between tension and compression, but the profile is the same. If I'm talking about the true values, if I want to draw engineering values, it will be like this. If you remember شفناها بيكون في inflection point if you remember وبيصير في fracture آخر شيء. So this is the engineering curve, and if you want to draw the true curve بتكون very close للtension curve but without necking point. Okay. هلا هيدي البارت ما بتهمنا بالاناليسيس because why? Because we are just talking about now elastic region and how to determine the yield point. Okay. But in case they ask for us to represent the total profile for the engineering curve, بيكون عندنا like a point of inflection. And if you remember why we have this effect, and if you remember when we did the analysis, first when we go to the plastic region, it will be easier to deform. So for a certain period, the slope will decrease. But after this, the slope will become to increase. Why? Because look, you have the two plates that are compressing, and you are compressing a specimen between two plates. What will happening is that the cross-sectional area will tend to increase. But with contact with the plate, you have friction that will oppose increase of the area, which will lead to give you the following form. And you will have here the smallest area because you will have resistance to area increase at the plate. And it's like the plate are welded to the specimen, or they are nearly 1/4. And they will oppose any due to friction between the specimen and the plate. They will oppose the increase in cross-sectional area at this level, which will create a resistance, a resistance force, okay? So more you compress, higher will be the resistance force to increase of this cross-sectional area, and higher will be the load F needed to continue your compression. This is why after, as a first step, the dominant effect will be the effect of transition from elastic to plastic, which make it easier a little bit to deform. This is why the slope decrease first. But after, the resistance effect at the plates level will be dominant. This will cause a re-increase in the slope after until fracture. Okay, so this is how we do the analysis of inflection point in the engineering curve. Now in the true curve, we don't see this. Why? Because in the true curve, we do sigma over not A0 over the actual area. And the actual area is, if you want, if you take you have two effects. You have the effect of force increase, but at the same time, you have effect of area increase. And both are increasing, but the area increase, the area rate of increase is overcoming the rate of increase of sigma, of F, sorry. So it's F over A, over actual area. F is increasing a lot, but also A is increasing, if you want, at A, the slope of increase of A will be dominant. This is why in the true curve, you will go back to the profile you are familiar with in the tensile, and you have the strain hardening zone. But instead of having necking, it will continue, the strain hardening behavior will continue until rupture. Okay? This is why when we draw the engineering and true curves in compression and tension, we say that we have the same behavior except the necking behavior. Okay? While the engineering curves are very different because due to the variation of force is different, because here the resistance effect at the plate level to increase of cross section will add another factor to force increase. Now, in order going back to epsilon yield, okay, to calculate epsilon at yield point, what we should do is the following. We have calculated sigma yield. They gave us the elasticity, the modulus of elasticity coefficient. The modulus of elasticity is the slope of this line, the straight line that we have drawn here. So what can we see from this? Since the slope of this line here is E, then we can say that the modulus of elasticity E is equal to delta of sigma over delta of epsilon. Okay, and in this case, the 2 points of interest are first the point here, which corresponds to epsilon 0.002, and since it is on epsilon axis, the value of sigma is 0. And the second point is the yield point, characterized by sigma yield and epsilon yield. So we have that delta sigma is equal to sigma at yield minus 0 over delta epsilon, which is epsilon yield minus 0.002. Okay, so if I rearrange my terms, my unknown is epsilon yield, so I can get that epsilon yield is equal to sigma yield over the modulus of elasticity plus 0.002. Okay, so from here I can get the value of epsilon yield needed, and this is the engineering value. Okay, so once I have the engineering values, I know that to calculate the strength coefficient and strain hardening exponent, I should base myself on true values of stress and strain. So now I have to, I can do two things. First, I can go to the formulas which correlate epsilon true to epsilon engineering and sigma true to sigma engineering at epsilon engineering and apply them. So this is the easiest straightforward method because already I have sigma yield at engineering. So I calculated sigma yield engineering, and I calculated epsilon yield engineering. So using these formulas, I get epsilon true at yield and sigma true at yield. Okay, and once I do this, I get the characteristics of the first point. Okay, now you will see that for the yield points, the true and engineering values are very close to each other. And sometimes as approximation, they take the same values because they consider that in the linear region, the variation of between engineering and true values are very close. Why? This is due to what? This is due to very low values of epsilon in the elastic region. The elastic region is characterized by very small values of epsilon. This is why you can demonstrate that epsilon true will be very close to epsilon and sigma true will be very close to sigma engineering. And to verify this, we can do it by calculation. Okay, so here, so as we did, the first step, I calculated sigma yield by dividing by A0, okay, which is pi d square over 4. Here square is missing, so let me add it. It's pi d square over 4, okay. Now, once we get sigma yield, the second step is to get epsilon yield. So to get epsilon yield as we did, but here just for you to make it clearer, this is delta epsilon, okay. So they calculate first delta epsilon, and then they added to this delta epsilon, which is yield over elasticity modulus, they added 0.002 to take into consideration the offset. So we have the value here of the engineering strain at yield. And now we have two methods to calculate the true values. Or we use the previous formulas we have seen together now, or we have another option. We can calculate using the initial formulas. And you know that in compression, epsilon C, epsilon compression, is ln of H0 over H. Pay attention here. Why I considered the opposite? I put compression. If I don't put compression, I just put epsilon, هتكون negative value, بتكون ln H over H0. But when I put epsilon compression, and I want to take the absolute value, then I should take the opposite, ln H0 over H. Okay? So if I want to calculate based on this formula and not on the other formulas, not on epsilon true equal ln 1 plus epsilon engineering, if I want to use this formula, then what I should do, I should calculate the new value of H. Okay? And to calculate the new value of H, I can simply go back to the definition of epsilon engineering. I have that epsilon engineering compression, okay? Because I put C and I do this. I do H0 minus H over H. And since I got already epsilon compression, I calculated, and I have the value of H0, I can deduce the value of H. And as you can see here, H is very close to H0. Because as I told you, in the elastic region, the variation in height will be very small, okay? This is why epsilon true is nearly equal to epsilon engineering. And you can verify this in the calculation. So nearly it will be the same value. Now, once I found the new value of H, I can calculate the new area because I know that I have conservation of volume. So I do, and they said, assume that the cross-sectional area is the same. In any case, I have conservation of volume. Conservation of volume is always applied, okay? But in order to say that the volume is 8 times L, this means I should have uniform cross-sectional area. And in compression, it's not true, but this assumption can be done before big deformations. The final shape will be like this if you want, okay? Because at the end, you have resistance to increase in cross-sectional area. But as you go to the center, it will be more uniform. But since they said here to neglect this effect, we can assume that the volume can be calculated as cross-sectional area times the length. And we assume uniform cross-sectional area over this pattern. So since the volume is conserved and we know the initial volume, it's A0 times L0, we can, based on this, say that A0 L0 is equal to A times L. So we can calculate the new value of area. Area is equal to A0 L0 over L. And therefore, once we obtain the new area, so this is a second method to calculate the true strain. The true stress, sorry. So true stress, you can calculate it as, so here true stress is the force, the load at this point, which is given to be F equal to 140,000 lb. You divide it by the actual area, which is calculated based on this formula, and you get then the true stress. So, but this method is complex relative to the other method. If you use the other method, it is easy. Okay. Sometimes they force you to find the area. If they ask you, for example, to calculate the new area, you should do this method. Okay. But if they don't ask about the area, just you need to find the true stress. You can use the formula relating engineering stress and strain to true stress and strain. Okay. Now, until now, we have found all information for yield point. And for yield point, we have the true stress and we have the information about the true strain. The true strain is very close to the engineering strain because, as you can see here, the height h is very close to h0. This is why they used here the same value for epsilon. Epsilon engineering nearly equal to epsilon strain. To engineering strain. So what we will do now, we need the information for the second point. For the second point, they told us that when we apply a load of 260,000 lb, okay, we have a new height. The new height is 1.6. So for us, if you want, since we know the new height, we can calculate the new area based on the conservation of volume. So based on the conservation of volume, we can say that the new area is A0 times L0 over L. Okay, A0 is already calculated, and we have that L0 was 2, and the new length is 1.6. So by using this formula, we can get the value of the new area. And getting the actual area, the true stress is simply calculated as the force over the actual area. So we get the true stress at the second point. And for the true strain, okay, we take ln L0 over L, and I repeat again, it's L0 over L because we are taking the absolute value. And we just put true strain epsilon compression like this. Then we just consider the absolute value. And once we have the characteristics at the 2 points, now we are ready to calculate the value of the value of the strength coefficient and the strain hardening exponent. We know that the flow curve should satisfy the following relation. The true curve is sigma true equal to K times epsilon true to the power n. So the two points should verify this equation, which will give us two equations. Okay, so the first equation will be by applying this equation to the first point. The first point is characterized by sigma equal to 78862 equals to K, which is unknown and we want to find it. The corresponding value of epsilon is 0.00464 to the power n. This is equation number 1. Equation number 2 will be, for my second point, I have the characteristic sigma equal to 117714 equals to K times 0.223 to the power n. So now, this is equation number 2. So now, in order to get n, we can divide 2 by 1. Okay. So if we do here equation 2 over equation 1, you will get the following. K will be simplified because you have K here and K here. You will get for the first term 117,714 over 78862 equals to the ratio of, since you have power n for both terms, so you can take n in factor. So it's 0.223 over 0.00464 to the power n. So to solve for n now, you can linearize this equation by doing ln for the two sides. Okay. So if I do ln of the first side, it is ln 1.493. And for the second side, when I do ln, n will be, you will have n times ln of 48.06. This equation will give you the value of n. Once you solve for n, you can use one of the 2 points, or the first or the second, to replace in the equation sigma equal k epsilon n to get the value of k. So k, for example, here they selected the second point. So it is sigma 2 over epsilon 2 to the power n. They got the value of k. And of course, the unit of k is the same as the unit of sigma, which is lb per inch square. Okay, and therefore, once I find the values of k and n, then I can find the equation of the flow curve, which is of the form sigma equal to k times epsilon to the power n. Any question on this problem? Ralph, concerning the height, which part, Ralph? In the yield, you mean? The calculation of height in the yield for the yield point? Okay. Look, once you calculate epsilon, here you understood how we found epsilon engineering here. It's fine for epsilon yield, how we found it. Once you find epsilon yield, okay, you go back to the definition of epsilon yield, okay? Epsilon yield in compression is what? The engineering value. It is, because I take epsilon yield compression, so I take the absolute value. So it is H0 minus H over H0, okay? So here you have calculated the value of epsilon yield. The value of epsilon yield is 0.00464, okay? Equals to H0 is given. It's equal to 2. Okay. If you want here, you can, if you divide by H0 here, what do you have for the second term? It's 1 minus H over 2, okay, which is H0. Now, in order to calculate H, you can calculate H from this equation, because you can deduce that H over 2 is equal to 1 minus 0.00464. Okay, so H is equal to 2 times 1 minus 0.00464, and you will get a value of H very close to H0. You get 1.99. So here, if you do the calculation, I think the value is given here. Yes, it's 1.99 something. Okay, so this is how you calculate the value of H. This was your question or something else? Okay. So just it is based on the formula. Once you write the formula and you apply it, you can get the value of H at any point. And here we did it at yield. You can calculate it also for the second point. If you want to calculate H, you can use the same method for H calculation. Okay.
Doctor?
Yes.
Here they calculated the true stress and strain from the formulas used to calculate the engineering stress and strain, right?
No, here, no, look, they used, and they didn't use the relation between engineering and true values, which we did in the previous problem. They went back to the initial definition. What is the definition of sigma true? To define sigma true, okay, it is the force over the actual area. So what they did is they calculated the actual area of the specimen, and they divided the force by the actual area to get sigma true. And to get epsilon true, also they use the definition. What is epsilon true? Epsilon true compression is ln of h0 over h. So they got the value of h, okay, and based on, and here for example, once you calculated epsilon engineering, you were able to calculate h, and once you have h, you can calculate epsilon 2. Of course, here they did a long method. It is easier for you once you find the engineering values to go back to these formulas. It will, and you can try. It will give you the same results. So if you go back to these formulas, knowing epsilon and sigma engineering, you can get sigma true and epsilon true. So these are two different methods, and both will give you the same result. Okay.
Okay.
You can try if you want to use the second method and see that it will give you same answers. Any other question before we continue? Okay, so for concerning the Brinell hardness problem, so we have already solved this problem. Just I want to stress out units, so pay attention for units. This is the only challenge in this case, because if you use wrong units, you will get a wrong result. Okay, so pay attention that the force, it's a force, but the value is in kilogram. Why we can do this approximation? Because here the force represents what? Represents the weight. It's related to the weight of the ball used in the task. And you know that the weight is proportional to the mass. So the weight is m times g. Okay? So we can, to define the weight, instead of giving its value in Newton, we can give the value of the mass. So in case they gave you the weight of the ball instead of its mass, you should pay attention to divide by g in order to get the mass, and then replace not by the weight but by the mass. Okay, so this is for this problem. Now,
دكتور
yes,
مش إنه if they give us the mass we multiply it by g and we put it
no, we keep it as mass. F is
we
in
should keep it
kilogram.
as a mass.
Yes, because F is the load in kilogram. Pay attention
Okay.
for this. Never put Newton. Never put the value in Newton here, because it will give you wrong
Okay.
results. Okay.
Okay, thank you.
Now for the last problem in this chapter, a 125 millimeter diameter shaft rotates inside a stationary bushing whose inside diameter is 125.6 millimeter and length is 50 millimeter. In the clearance between the shaft and the bushing is a lubricating oil whose viscosity is 0.14 Pascal second. The shaft rotates at a velocity of 400 revolutions per minute, and this speed and the action of the oil are sufficient to keep the shaft centered inside the bushing. Determine the magnitude of the torque due to viscosity that acts to resist the rotation of the shaft. Concerning G, Karim, you can take, it's fine, yani. In general, take 10, okay? You can take 10, because the error will be very small, okay? So now, when we read this problem, it might seem complex, but if we draw a small figure, you will see that it is simple. So let us draw the figure here. We have an inner shaft, and the radius of the inner shaft is given. The radius is 125 millimeters. And this shaft is rotating inside an outer bushing that is fixed. It's stationary, it's not rotating. So this is the bushing. And the diameter of it is given to be 125.6. Okay, so now knowing this, we can determine the clearance in between. So the clearance between the two is 0.3 millimeter, because what we can do, we subtract 125.6 minus 125, we get the total difference. We divide by 2 because we have the clearance from the two sides. So this is the clearance and the value of clearance is 0.3 millimeter. Okay. Now what is happening is that the inner shaft is rotating at 400 revolutions per minute. So omega is given. Okay. So this is, I will call it omega inner, is given to be 400 revolution per minute. Now omega outer is 0 because it's stationary bushing, so it's 0. Okay, and we have oil in between. So here in between we have oil, okay, which is a viscous fluid, and they gave us the viscosity of oil. Oil viscosity is there. Now, and also we have the length of the system. So the length is 50 millimeters. So if you want, it's like cylinders of, and the total length is 50. Now, what they want us to find is the torque resulting from the viscosity that acts to resist the rotation of the shaft. You know that viscous effects will oppose variation of velocity inside the fluid. And here, what is happening is that we have velocity gradient in which direction? In which direction we have velocity gradients here? Yes, in the radial direction, exactly. Okay, in the radial direction, you have variation of velocity. You have 0 velocity at the outer bushing, and you have a linear velocity here that can be calculated. How you can calculate the linear velocity at the internal shaft? Which formula you will use? So V is varying in radial direction. From 0, okay, from, if I consider from 0 at the outer side, at the outer bushing, to V inner, to V inner. How to calculate V inner? If you know the angular velocity of rotation, the linear velocity is related to the angular velocity by omega inner times the radius. So the strategy is first to calculate the linear velocity. Once we find the linear velocity, we can calculate the shear stress. Why? Why we need the shear stress? Look, how should I think here? They told me to find the torque acting, which is due to the viscosity effect that is resisting rotation. The torque is proportional to what? To find the torque, I need the force, okay? Because the torque is F times radius. And the force is proportional to what? The force is proportional to the shear stress. The force can be calculated as shear stress tau times area of shear, okay? So to find F, I need tau. And to find tau, I will use the formula that tau is mu times del V. Here, if you want, we can say in the course we have seen del V by del Y. Here, because it's radial, we can say del Y by del R. Okay? Or you can name this Y as you like. Okay? So now our purpose to find the shear stress is to determine this term, the variation, the del V by del